Okay, we're back again. This time we're looking at a couple of series here, and we're going to talk about a different idea called conditional convergence. Just want to remind you. Okay, well, first let's do an example here. We have conditional convergence if the series that we're looking at does not converge without the negatives included. In other words, if a series, for example, like this one, we all know what this is. It's harmonic series, and it's divergent. But we saw in the last example that we had this. And last couple of examples, I think this happened. This turned out to be convergent. So this is an example of a series that is conditionally convergent, because without those negatives in there, it would not converge. So it's called conditionally convergent. And this one up here, as we can see, even without these negatives, the alternating negatives, this series would converge. It's 1 over n squared. It's a p series. So by putting negatives in, which are shrinking in size and magnitude, it just makes the series converge that much faster. So we have this concept of what's called conditional convergence or absolute convergence. So this is a series that would be absolutely convergent because if we looked at the series of positive terms, ignoring the negatives, in other words, if we took this, this is n plus 1. And if we took that, that would converge because it's really just this. It's just this. So that's convergent. And there's no question this convergence, P series, P equal 2. So this series would be considered absolutely convergent. We wouldn't even have to look at the alternating series test for this because this series converges. So now let's talk about this next one down here. This one, so we would say absolutely convergent. This one down here, let's look at the series of positive terms. If we looked at this, I'm just going to rewrite this because it's a little unclear. Okay, so here's our series. And if we were just looking at this, we've seen this before. We know this is divergent. It's roughly a P series. We could use the integral test on it. We could possibly use we could shift the index a little bit and identify it. I mean, it's the same thing as harmonic series, but it's lost a couple terms because the first one, remember, if we just looked at this, we would see the first few terms. We'd have 1 over 5 plus 1 over 6, etc. So it's a harmonic series minus the first 4 terms, 1, 1/2, 1/3, 1/4. It's still going to be divergent. Just without those first 4 terms, it doesn't change it. It'll be divergent. Anyway, so that's divergent. However, if you look at this series as an alternating series, we see that number 1, the limit of the a sub n, which is this, does equal 0. And number 2, the a sub n plus 1 is less than or equal to a sub n. I think it's pretty clear. Again, we could show some of that detail. A sub n plus 1 is 1 over n plus 5. And is that less than or equal to 1 over n plus 4? I think it's pretty clear that we wouldn't have to do a lot of work to show that n plus 4 is less than or equal to n plus 5. And 4 is less than or equal to 5, all n. So we see that with these two results, that this series would be convergent. So what we have is a conditionally convergent series. That's what we would call this. So we already saw by AST that it converges, but we would also say that if we needed to, that it was conditionally convergent. Condition convergent. Okay. Conditionally convergent. So that's the idea. Let's see. Let me just pick another one here. I don't want to make this video go too long, but let's see. Here we have another one. We can see that it's alternating. First condition, n goes to infinity. 1 over n root n. It does equal 0. Number 2 is a sub n plus 1 less than or equal to a sub n. Well, you'd have to check it. 1 over n plus 1 root n. Is that less than, sorry, root n plus 1. Go back here. Let me get rid of that. Okay, so we have a root n plus 1 here. Question is that less than or equal to 1 over n root n? And I think it's pretty clear that it is. We could go through some algebra here to demonstrate this, but we won't on this one just because it's going to take too much of our paper. But and it would be, you cross multiply and you get a few things to cancel out for you here, but maybe we could square both sides. We can get n squared n and an n plus 1. This would be 1 n squared. So that would be 1 plus 2 is 3. Yeah, we squared both sides. And you see here that you do have a n cubed, and this would be n cubed plus 3n squared plus 3n plus 1, which means you would have this equation or inequality to solve. And I think you can see that that's going to be true no matter what n is. This right-hand side is positive for positive n. So, I mean, our suspicion was correct. Anyhow, I won't do that again because it takes too much time, but you should be sure. So what we have here is, by the AST, we have convergence. Okay, so all of this together shows us convergent by AST. Now, the problem is it conditionally convergent or absolutely? Well, let's look at the absolutely convergent. That's the question. Well, you'd have to look at this series. Ignore the negatives. You'd have this 1 over, it looks like n to the 3/2 when you look at it without the radical. So you have a p series, p greater than 1. This would be convergent. So we do have absolute convergence. Absolutely convergent. Okay. Now let's go down to this next one, D here. You could see that if this were just, if it didn't have the negative, we have this. Okay. And that's by, we could probably do a limit comparison on this one. Not too difficult if we compared it to 1 over root n, 1 over root n plus 4, and you found that limit, you would see this is the same as the limit as n goes to infinity. What is that? Root n plus 4 over the root n, which is this. You have that root 1 plus 4 over n, and that equals 1, which shows that both the series are divergent. That's one way you could do it. Again, we saw that this could be viewed as a p-series if you shift it a little bit, and then you could, with that little bit of algebra, you could show that it's, let's see, well, let me just write a couple of terms there. You've got 1 over square root of 5, 1 over square root of 6, etc. But you can see that that's just this series, n equals 1 over root n minus the first 4 terms that were over here. Minus, in other words, we'd be minusing the 1, and the 1 over root 2, and the 1 over root 3, and the 1 over root 4. So this itself is a p-series with p equal to a half, and it's going to diverge, and subtracting a finite number off of it won't help it. It won't change that divergence. So that's another argument. You can say it took us just as much work to do that as it did to use the limit comparison test up here. So this was divergent by LCT. So I used to say that they're both divergent. Anyway, it's not absolutely convergent. That's what this tells us. Okay, so fact is, when you look at this problem, you'll see that number 1, though, the limit as n goes to infinity for this 1 over root n plus 4 does equal 0. And number 2, we have a sub n plus 1 less or equal to a sub n, yes or no? Well, you could start with this, n is less or equal to n plus 4 for sure, and then 1 over root n. Well, this would be n. Well, I take that back. Let me go back here. Get rid of that for a sec. Let's try that again. Let's start with n plus 1 less than or equal to n plus 5. Yeah, okay. So that is that's not what I wanted to do. Let's try that again. Okay. Here it is. What we're trying to show is whether or not that the next term is less than or equal to the first term, non-increasing. So we got the 1 over root n, n plus 5. Is that less than or equal to 1 over root n plus 4? That's the question. Well, if you square both of these, and let's take a couple steps at a time. N plus 4 would be less than n plus 5 after we squared them. And it's obviously true all n. So the point is 1 and 2 of the AST theorems are met, these conditions, and that means you have convergence by the AST. So all that tells us that it is basically conditionally convergent. Okay, so this is starting to become a long problem. Well, it's several problems at once, so I think we'll come back to this on the next video because it's becoming way too long here. So we'll finish this one up now and we'll revisit these.